Yeah, good morning. Today we'll discuss the class relations because it's really a foundation for many methods for solving problems of proving theorems. For example, here I list a few of them. Counting and two important techniques for designing algorithms, namely divide-and-conquer technique and dynamic programming. So they are based on recurrence relations. In terms of techniques for proving things, the well-ordering principle and the well-known mathematical induction, which you learned in high school. And we'll discuss it in this course as well, mathematical induction. There are all these things based on recurrence relation. So here is the most famous example of recurrence relation, namely Fibonacci number. All right. So here are the sequence of numbers called the Fibonacci sequence. Start with 0, 1, 1, 2, 3, 5, and so on. And this sequence can be defined by this recurrence relation. Fn equal Fn minus 1 plus Fn minus 2 with boundary conditions for the first two values. So these two values are initial conditions or boundary conditions. So this recurrence relation together with these two initial conditions uniquely specify this sequence. And any Fn can be computed using the previous two numbers. So this is recurrence relation. A recurrence relation is we define a value of n, so P of n is a value in terms of previous values. So this is the basic idea of recurrence relation. So here the value of Fn is defined in terms of the Fn minus 1 and Fn minus 2. So that's the recurrence relation. Okay, it's very, very simple. So today I will give you quite a few examples to obtain recurrence relations. And then we'll use recurrence relation to solve problems. So eventually we need to solve problems, either to prove something, such as it will be mathematical induction, or well-ordering principle. I think I will discuss well-ordering principle today and discuss mathematical induction on Wednesday. All right. So I will touch these examples, or application of this technique, recurrence relation. Later on, when we discuss counting, we'll get more into recurrence relations in order to count things. All right. Okay, counting is very important. Okay. All right. So everyone knows Fibonacci number, so it can be defined in this way, all right? Okay, so let me give you a few examples. All right, perhaps one example on mathematical induction, which you are familiar with. Summation of first n order numbers. So we will come on computation to compute this one. All right. So one way to obtain a closed formula is to use recurrence relation. So suppose this one we denote as Sn. All right. Now Sn can be represented as Sn minus 1 plus 2n minus 1. So that's the recurrence relation for this summation. We can obtain this summation. So one way to solve this recurrence relation, which we'll discuss in next week, how to solve recurrence relation. All right, we'll be able to get a closed formula of S of n. For this one, of course, if you recall, this sum equals n squared. All right. Now, typically in high school, maybe we ask you to prove this one using mathematical induction. So when we use mathematical induction, we assume this one holds. So it holds for n minus 1. Okay, actually, in general, we can assume it holds for everything less than or equal to n minus 1. But for this particular one, this one will be good enough. We assume this sum holds for this. Then we'll try to prove this one also holds for n. So in this particular case, so in mathematical induction, actually we implicitly use this recurrence to prove that it also holds for n. So what we do is by induction hypothesis, we know this one, so we can assume this one is known. So this one is n minus 1 squared. All right. Now we use this recurrence relation actually to prove Sn equal n. So we use this recurrence relation. Okay, so this one will give us n squared. So in mathematical induction, we implicitly used recurrence relation. So in this particular case, we implicitly use recurrence relation in order to prove Sn equal n squared. Every mathematical induction actually use an implicit recurrence, or eventually actually it is explicit, but normally we don't state it. So for this particular problem, we use this recurrence relation when we use mathematical induction. All right, so see the recurrence relation really come into play for many situations. So here is for mathematical induction. Of course, this one, there are easy way to prove that their sum equal n squared. One way is to look at this. Look at an n times n grid. One way to do it is you look at this, okay? Okay, now first term, here's 1. And the 3, this is 3. This is 5, this is 7, this is 9, this is 11. So of course, the summation equal n times n. That's another way. Actually, maybe it's easier, more intuitive. Okay? All right, but that's a different story. Just like a Fibonacci sequence, quite often you see, especially in IQ test, you will see this kind of problem. I give you a first few number of a sequence, ask you to obtain next number. For example, I give you 1, 2, 3, 4, I say 6, 9. Okay, let's see. 6, 9. So ask you next number. All right. Actually, you can write any number. And if you can give a formula, you can convince that indeed the pattern holds. But if we just look at 1, 2, 3, 4, 5 without these, the next natural number, maybe next one should be 5. But with these numbers, what will be most natural number here? Actually, it can be anything. You can always find a formula to show that indeed this one, whatever number you get, makes sense. Because relative number depends on initial numbers. All right, you can always write a formula. But in case, but there's something more natural maybe. This one only maybe involving first a few terms. Say suppose this one, if I tell you this term always depends on, this one, an depends on So an minus 1 and a minus 3 only depend on these two terms. So we want to determine this number. Actually, in this case, it can be uniquely determined if I told you so. Okay. So in this condition, we can see. So 3, this one, actually, these are initial ones. These are initial conditions. Because 3 will depend on this one and this one, but this number is not known. But for 4, we know these two give us 4. And 6, these two give us 6. Now we can find a pattern when we do such things. So we will see actually 4 equals 1 plus 3, 6 equals 2 plus 4, 9 will come from 3 and 6. Oh, it's at the sum of these two. 13 is 9 and 4, so it's just sum. Then very naturally, this number, if I say just take down these two, you will see 19 come from these two. All right, so this one actually gives us the following recurrence relation. This an can be expressed as an minus 1 plus an minus 3. With initial condition, A0 equal 1, A1 equal 2, A2 equal 3. Typically, we say this one is start with 0, A0. Okay, because natural number starts with 0. But if you don't like 0, you want to start with A1, then it's also fine. You can say this is A1, then it's A2, then this one is A3. But then be careful with initial conditions. So that will be A1, that will be A2, that will be A3. Okay. So really, it's sometimes we include 0 for natural number. Some people don't. But usually in mathematical field, we include 0 as that natural number. But in engineering discipline, sometimes we don't. Many people may don't like to include 0 as natural number. Natural number starts with 1, but that's okay. Whatever we do, whatever you do, you need to be careful when you write initial condition, whether A0 or A1 here. Otherwise, it will be uniquely determined. All right. Now you see, we can get the initial condition and the recurrence. Once we recurrence, we'll be able to compute every number. So here, next number will be 28. So this is close to 4, right? And so on. So this sequence can be uniquely determined by this one. And we can use this recurrence to compute this sequence quickly. One way is just use this one, another way to find the closed formula. But in terms of time for computation, closed formula may not be helpful, but which is out of our scope. Okay. All right. So this one. Okay. Now it's very important about initial conditions. If we change this initial condition, the whole sequence will be totally different. So suppose if instead of this one, if I start with use different color. If I start with this one, then the sequence after that will be totally different from these, right? So naturally, then this one will become 3, this one will become 3, then 5, then 8, then 11. So you see, actually Fibonacci number here, not really. So here looks like Fibonacci number 5, 8, 11. Of course, next one is different. It's 16 now. All right. Okay. Now, yeah, let me give you another one similar to this sequence. Let's see. One, 2, 3, 4, 5, 6. What will be next number? Of course, naturally it should be 6. Okay. Now, of course, it can be something else as well. But if I told you again, so it's called this Bn. If Bn depends on the first, also on 2, if Bn depends Bn minus 1, Bn minus 3. If I also tell you this, what should the next number? Okay, give you maybe 1 minute to see whether you can obtain it and the translation from this one. Okay. So actually, we can uniquely determine this by solving a system of equations. So look at these two values. When it uniquely depend on this. So suppose it's so alpha Bn minus 1 plus beta Bn minus 3. So Bn equals this one. All right. Now for this one, we know it's 4. So 4 equals this one. So it's n minus 1 is 3 alpha plus beta. When we look at the 5 equals 4 alpha plus this one, okay, 2 beta. So we can uniquely solve this equation. In this case, this equation has a unique solution. Alpha equals 2 that's the value of alpha. All right, now we can get the translation, which is all right, so this can give us the translation. So once we have this one, of course, we can naturally compute it. So the interesting thing is next number, if you compute next number, it will be 6. Then next number will be 7, will be 8, will be 9, will be 10. So it's kind of surprising. The sequence looked like a natural number, sequence of natural numbers. Now you may wonder, actually, is this one really same as Bn equal n? So if I start with 0, then if here is 0, then it should be n plus 1. Okay. Otherwise, so if it starts with B0, otherwise, if here it starts with B1, B2, then it will be Bn exactly equal n. Otherwise, if this one is B0, here is B1, here B2, then Bn equal n plus 1. So you may wonder, this was same as the sequence? Actually, it is. So that means it may not be unique to represent the sequence by the translation. We can represent it in this way. So this one without the cleanse, we can also close the formula. Maybe I should not say uniqueness here. It's nothing to do with the translation is unique here. But anyway, this one actually same as this one. So there may be easier way to represent it. Okay. So initially, based on the current relation, that's what we get. But incidentally, it turned out to be the sequence is just Bn equal n plus 1. Okay, or just Bn equal n if we start with B1, B2. Okay. All right. So that's the current sequence. Recurrence is also very, very closely related to counting. So let me give you some examples on counting. All right. So I give you two types of tiles and want to tile a strip of length n. So here length n. So I put tiles on this strip. I want to know number of different ways. To tile this strip. Okay. So of course, if just length one, of course only one. If length two, there are two different ways. I can either just use this tile or use first tile twice. So there are two different ways. So what is three? Number of different ways. Of course, for three, you can try all possibility because number very small, right? Since number very small, you can try all possibilities. So can this one start with this one, followed by this one. So this gives us one way. Or I start with this one, followed by this. Another way is I start with this one, followed by this one, then next one is this. So that gives us three different ways. We can do it exhaustively, but in general, and we cannot do it in this way. Just too many. One way to do it is use recurrence relation. Okay. Now, how many different ways to tile this? There are two ways to start it. Either we start with this one. We start with this tile or with length two tile. So give us two different ways. So once we start with this one, number of different patterns is number of different pattern for length n minus 1. So here will be n minus 1. Here will be n minus 2. So this gives us a number of different patterns in terms of previous values. So dn, so number of different ways. If we start with this one, it's dn minus 1. So here is number of different ways for length n minus 1. So here dn minus 1. Now here are different ways for n minus 2. So this gives us recurrence relation. And here give an initial condition. So this one, together with this one, will enable us to determine a number of different ways. Of course, if you want to find a closed formula for d of n, we need to solve this recurrence relation, so-called to solve the relation. In next week, and maybe the week after as well, we'll discuss how to solve this recurrence relation to get a closed formula for d of n. dn, okay? But the main focus of today is to focus on how to obtain a recurrence relation. So you see this one actually very, very closely related to Fibonacci number. It's just Fibonacci number shifted by 2 positions, okay? All right, so it's quite simple here. Quite simple here, okay? Now let's change something. Now suppose my tile has pattern on it. Suppose this one look like this. All right, now this one maybe look like this. Now I'm asking same question, how many different ways to tile this one? Of course, different ways mean different pattern can I obtain for this strip of length n minus 1. All right. Now, this one, does this one hold? Okay, now what happened is first, let's take a look at initial condition. That's always useful to start with the very beginning, the initial condition or the boundary condition to see for very small value to see how it works to get a feeling. Now for n equal 1, initially there's only one way, but now there can be two ways. The tile can be used either this way or we can rotate it. Here 90 degrees gives us actually two different patterns, either this way or this way. Just give us two different patterns, right? Or maybe this one I change it. Otherwise, it's okay, but maybe I just change it. Instead of this one, still, no, this one does not help. It still give me 2. It does not matter, okay. Still give me 2, okay. I want to keep it 1, so yeah, okay. Let's use this one, then it will be 1. Otherwise, the curve does not look to be too interesting, maybe in the middle. Okay, this pattern looks like this, okay. Now for this pattern, rotated does not help, only 1. So for n equal 2, we can either use this one, whether this one are rotated at 180 degrees, it's still same, so only one way. Or these two. Now I can use combination of these two different patterns. So I use these two. But each here will be 2 possibilities, here will be 2 possibilities, actually give us here 4 possibilities here. 4 possibilities. 4 different patterns. Okay, so initial value now changes. So if it's called, maybe it's called alpha D, or maybe just called G, okay. So we know G1 equal 2, G2 now equal 5. All right. Now in terms of recurrence, we can start with this one or this one. So it will be summation of this part. So basically it still look like this. Gn will be summation of here Gn minus 1 plus Gn minus 2. Okay. But now the difference is coefficients here. If I start with this one, a square, but not initially for the previous pattern, there are only one way, but now we have 2 different ways. So here will be 2 times this one. But for this pattern, whether we rotate or not, it's still same, so still 1. So here it will be still 1. All right, so the constellation will be this one. This one plus this one. This is the constellation of pain with this initial condition. So we get a different reconciliation. All right, okay. So let's show you an idea how we can use it for counting. Now, a more difficult one is the following. Okay, but these two are fixed. So I cannot break it into 2. Okay, just one piece. The pattern look like this, right? There's 2 different patterns make this one. This one actually, the counting problem based on this one is much more difficult. So this one give us, for length 2, this one give us 2 different ones. I can rotate 100 degrees. So either this one, for this one, there are 2 different ones. Or this one. Okay. So it seems quite easy. So based on this one, the only difference is, so suppose I still use G, maybe use G star on this pattern. So this pattern star, okay. So there are 2 different ones, you will put 2. It seems to be very simple. But the answer is not. This is incorrect because just for length 2, For length 2, one way is to make it like this, one way is to use 2 of these. 2 pieces of this. So, but these 2 are same pattern. We cannot count it as 2 different patterns because they are all 1 pattern, not 2 patterns. So they are overcounting here. So we have to be careful when we do this. Later on, when we discuss counting, when we come back to this problem to show you how we can do it carefully. It's more involved than this one. We cannot say do it in this way. This one actually is same as we use strings. Actually, you're locating. Four string, that's it, right? To form a string, bit string with length n, use these 4 different patterns. How many can we obtain? So you can encode this pattern. So in this case, we can use binary string to encode this pattern. And then the question is same as how can we form a bit string of length n, use these 4 different patterns. Okay. So I'm not getting into details today. Later on, we'll discuss it. Okay. So these are examples for counting. All right. For computer science, one of the most important application for the calculation or usefulness of the calculation is its connection with algorithms. Many algorithms actually are obtained based on the calculations. We use the calculation to obtain algorithms. So let me start with a very simple example. Suppose we have, say, 100 gold coins. All right. So each has a certain weight. So maybe 5 grams, or maybe 10 grams. But 5 is too small. Each exactly 10 grams. All right, 100 gold coins, each exactly 10 grams. So it's gold. It's very, very expensive. So the weight is very accurate, 10 grams. But unfortunately, one gold coin has a defect. So its weight is less than 10 grams. One coin, so one particular coin has a defect. So its weight is maybe 9.99 grams only, instead of 10 grams. So how can we find out this defective gold coin? Of course, we can weigh each of it. We do it 100 times. Right? We do it 100 times. In the worst case, we'll be able to find it. But it takes too much time. Suppose it's not 100, but 1 million. Certainly, it's too time consuming. Okay. A good way actually is based on recurrence. We can do it about 7 times, so-called ideal binary search. The ideal binary search actually is based on recurrence ratio. We only need it 10 times. So what we do is we have 100 coins here. We roughly evenly divide them. So 100 first time we can evenly divide them. So 50-50. All right. Now we just weigh these 50 coins. So pick one, maybe this side. We weigh these 50 coins. If their weight exactly equals 500 grams, we know the defective coin is on this side, is here. So if here is exactly equal 500, then the defective coin must be on this side. So if this one is less than 500, then we know the defective coin is on this side. All right. Now, depending on the result we obtain, either the original problem is to find one defective coin from 100 those coins. Now the problem is reduced to find a defective coin from 550 coins. All right. So original problem is based. The original problem say it's find the gold coin. So it's G100. So this one denotes the problem on finding. Now it's reduced to G50. So in order to solve this problem, we only need to solve this problem. So you see the recurrence. In order to solve this problem, we solve a smaller problem. How do we solve smaller problem? We use same idea. So suppose this way exactly equal 500. We know the coin is on this side. Defective coin is on this side. Now for these 50 coins, we evenly divide it again. So about 25 and 25. So here will be 25. We use same technique, same idea again. Then take 50 coins, weigh it. If it's equal to 250, so if this part equal to 250, then we know that the defective coin on this side. So we do same thing. So this idea of binary search is based on recurrence. So to solve this problem, we only need to solve this problem. And then this one reduced to G25 and then maybe G. So here it's not evenly divided. In the worst case, G13 and so on. So that allows us to find a defective coin with at most 5. Here actually exactly 5 weight. We only need to do it weighting 7 times instead of 100 times in the worst case. So you see the power of the recurrence relation. So this whole idea is based on the recurrence relation actually. So connection between. So here connection is between. Connection is between Gn and Gn over 2. All right. Okay. So that's a kind of toy problem actually for us, for computer science. It's a kind of toy problem. Another problem you are familiar with is sorting. So a practical problem is sorting. So-called the merge sort algorithm. It's a divide and conquer algorithm. It's based on divide and conquer idea. So in order to arrange, say, n numbers, say, in increasing order, we sort them. Say, okay, so here how many numbers do we have? 12 numbers. So in order to sort 12 numbers, what we do, we evenly divide these 12 numbers into 2 groups, so 6 each. So not matter how we divide them. So we maybe divide them in this way. Here 6, here another 6. All right. Now, in order to merge sort these n numbers, so it's a set of n numbers, a set of n numbers. So we evenly define this set into 2 parts. All right. Now what we do, just use same idea to sort these 2 sets. So merge sort. So here is okay. So merge sort S1, it will produce a sorted list of S1. Here we merge sort S2 to produce a sorted list of S2. So inside, whatever we do, okay, we can treat it as a black box. So here, this one, once we sort it, it will produce a list, which will be sorted. So if this is S1, this is S2. So eventually, when we keep on doing this, it will give a sorted list. So it will give a 1, 4, 5, 13, 28, 38. So for S1. Similarly, for S2, it will produce a sorted list, which is 7, 8, 13, 17, 19, 21. All right. So that's the calculation. And the algorithm for these n numbers depend on the algorithm, same algorithm for these S1 and S2 for these two small sets. So here's the recurrence relation. The recurrence relation itself does not necessarily to be a function. It may not be expressed as a function. It's a relation between large one in terms of and the smaller ones. Okay. So once we have done that, these two lists are sorted. How do we do it? We do use same idea. Use so-called in computer science we call recursion. Also for this one evenly divided, use same idea. So this one divided into half, we sort it. So this one divided into half, maybe half sort this one, and to produce two sorted lists. Then we merge these two into one. So that's why it's called the merge sort. Merge these two to produce a sorted list. So that will give us, say, S star to produce S star result. Now, the key points that this algorithm is efficient, much better than bubble sort or insertion sort, is because eventually we're dealing with merging two sorted lists. This is much easier than sorting n numbers because they're sorted. It's easier to combine them. We just compare these first two. Small one come first. So here will be 1, 4, 5, 7, 8, 30. Oh, there are two 13, but not matter. Or we can change 1 to 18. Okay. So it can be easily obtain the whole list in linear time. So 1, 4, 5, 7, 8, 13, 17, 18, 19, 21, 28, 38. So eventually that will give us the algorithm. It's a time obeys. And the running time of this algorithm obeys the recurrence relation. So this time for n elements, this one obeys relation twice n over 2 plus linear time. I will get into the detail of these things later when we discuss how to solve recurrence relation, because here it involves the big O notation. But it turns out this one will give us running time. Instead of n squared time, time is roughly n log n. It's much faster, n log n instead of n squared. So here we see recurrence come into play when we design algorithm. In particular here, divided count method. So that enable to speed up algorithm for solving problems. Okay. So we have a break, and after break, I'll give you a few more examples. Then discuss a technique called the well-ordering technique for proving things. Okay. So let's have a 15 minutes break. Okay. Oh, in terms of resolution, now the problem is I checked. Actually, I already use the HD option already. So that's the best Zoom can do for us. I don't know why they set the resolution so low, or maybe they also consider the broadband the bandwidth in case the resolution here is too high. Some of the end users may not be able to receive it on time, like in time, because it will be slow. I really don't know how to deal with this technical problem because that's the resolution Zoom is set for HD version. I checked. Yeah, I'm not happy with the resolution, but unfortunately, I cannot do anything.